So the tidyverse and TidyModels are really created with human readability in mind. So sometimes models will take a little bit longer than they would if you were to do the modeling in maybe another package or another language, but it's really designed to sort of lower the barrier to entry for getting into machine learning. So that's why I really appreciate it. Cool, so what we promised you in our meetup blurb, we'll touch on what tidy data are, tools for working with tidy data in R, the basic workflow of TidyModels, and creating your first models in RStudio. So what are tidy data? I'm not going to go into this in too much detail because Andrew's going to take us through a data cleaning setup. So just to sort of mention it, tidy data is where every column is a variable, just letting that sink in. Every row is an observation, and every cell has a single value. So within the tidyverse, there are a number of packages. So I've just shown the few packages that we'll be using today for our data cleaning steps. But you can actually import all of these packages by just calling an import of tidyverse. But you can also import them separately if you want your package loads to be a little bit faster. So there's more packages in this, but these are just the ones that we're going to be covering today. Cool, so kicking off with dplyr. So dplyr allows you to conditionally select variables, filter observations, compute new variables, arrange and summarize observations, and a lot more. It's kind of SQL-esque, and it has a lot of overlap with pandas. So really useful sort of getting your data into shape. So is tidyr. But with the additional benefit of tidyr allows you to pivot between wide and long data formats, nest and unnest observations, unite and separate columns, and deal with NAs. Again, has some overlap with pandas and Python. Stringer is a fantastic package, and it provides a cohesive set of functions designed to make working with strings really easy. So we're going to use it today for string manipulation. Forcats is for working with categorical data, and it helps you reorder and recategorize your categorical data and also group categories, which is super helpful. Okay, Magritte is the sort of vein that runs through all of the tidyverse and TidyModels. It's a package that provides a bunch of useful operators, but the most useful, in my opinion, is this pipe. So it basically allows you to seamlessly string together function calls. And so I'm just going to spend a little bit of time actually fleshing this package out a bit more, because this is going to be really important when we get into our data cleaning and modeling steps. So basically, the way it works is to call the function f on an object x. You would feed x forward through the pipe operator into the function. Let me see if I can get a pointer. Yeah. So x doesn't need to be explicitly called within the function. It's rather fed forward via the pipe. So cool story, bro. Why do we care? So in this example, we have log base 10 being the function that we want to call on the object x. So you would just feed whatever's on the left-hand side into the right-hand side of the pipe would be the final sort of function call. So where this really becomes powerful is when you have these nested function calls. So here, for example, we want to find the sum of A and B, and then square root it, then sign, and then log with a base of 10. And this is perfectly fine code. Like, this is perfectly usable, and we do this all the time. But what makes it really nice when you add pipes is that you can kind of string them together in a pipeline. So everything in red here is considered the left-hand side of the final pipe, and blue is the right-hand side. So each sequential call in front of the pipe feeds forward into the next function call. So here we would have, if we stop the pipe here, we'd have the square root of the sum of A and B. And then if we stop the pipe here and commented this bit out, we would have the sign of the square root of sum A and B. And then finally, if we just let the whole thing run, we'd have the log of everything that followed before. So this is a super lovely way to write code, because if you change your mind and you no longer want the square root, you can just comment it out and you don't have to worry about where your brackets are. You don't have to create any transitional objects. It's just super nice. Yeah, and this is kind of the lifeblood of Tidyverse. Cool, so let's get practical. I'm going to hand over to Andrew shortly. Basically what we're going to be doing today is a classification exercise. So we'll be classifying cocktails, a cocktails data set. So what this data set looks like basically is it has the recipes for several drinks. So a margarita, tornado, shandy, sex on the beach, etc. Many, many drinks and their recipes. So not just the ingredients, but the amount of each ingredient within the beverage. And then it has a class. So some of these are cocktail classics. So margarita obviously is a classic cocktail. Some would be classed as daiquiris, others as non-alcoholic drinks. And again, I just replicated this Sex on the Beach as a cocktail classic just to indicate that, obviously some categories will have more representation than others. So my favorite drink is the Bee's Knees. It's from Ferdinando's in Observatory. If you haven't been to Ferdinando's, go for the pizza and the Bee's Knees. It is the Bee's Knees. So we want to sort of know maybe, for example, what class does this Bee's Knees cocktail fall within? So that's the exercise that we're going to be taking on tonight. So before we get there, let's first import and clean the data using some Tidyverse tools. So Andrew, over to you.
Thank you, Astrid, for the introduction. So the objective with my section of this talk is basically just to get the data into R and then to do a little bit of simple data preparation. And as Astrid has already mentioned, we're going to be using packages from the Tidyverse. And a lot of the operations that I'm going to be applying are things that you can actually do already in base R. So they're basically being replicated in the Tidyverse. But in general, what's happened is that the Tidyverse versions of these functions are just a little bit more efficient and a little bit easier to work with. So for example, you can read in a CSV file using a function from base R called read.csv. But instead of that, we're going to be using this readr package, which is part of the Tidyverse. So I'm going to load that in. Readr provides functions that essentially are a mirror to those in base R, but they not only are more efficient, so your data is going to be pulled into R more rapidly, but they also give you what's known as a tibble, which is very much like a data frame, but it has a wrapper around the data frame, which just makes it a little bit easier to work with inside R. You're going to see examples of tibbles in just a moment. So the data, as Astrid has mentioned, that we're going to be working with is the cocktails data. And this actually comes from a really nice repository on GitHub, which is called Tidy Tuesday, and it's run by an account called R for Data Science. And the premise behind Tidy Tuesday is that every Tuesday they publish a new data set, a new open data set, and then the R community basically has a strong go at that data set and normally produces a range of really, really nice visualizations, which they are then published on Twitter. So the cocktails data is just one of those examples. I'm going to store the shortened URL for that data set in a variable called URL. And then I'm going to use the read_CSV function from the readr package to pull those data into R. And like this ends up being like a really long function call broken across many lines, but that's just because I've added in some commentary. The key elements here are providing it with the URL. So not only can read CSV read data from your local file system, but it can also pull data in directly from the URL. And then after providing the URL, I'm specifying the column types in the data set. Now the column types are actually not strictly necessary. You can just allow read CSV to infer those column types. And for the most part, it does a really good job of this. However, in the interests of having your CSV file read in the most robust way, it makes sense to just specify the column types once you know them. So I'm doing this in probably the most verbose way possible, specifying the name of the column and a corresponding column class. So for example, the name column is going to be characters. The the row ID is going to be a double. I guess that could also just be an integer. So this is one way that we can specify the column types. Another option is much more abbreviated, and that you can specify the column types as just a simple string with placeholders in that string. So for example, C is for character, D is for floating point data, and a hyphen is for skip. You can see that here I've actually skipped the column for the ingredient number. This is quite a nice feature. If you know that there are columns in your CSV data that you're not going to use in your analysis, then why actually pull them into R at all? So let's run that. Whoops. And you can see down here in my terminal, it's executed. We're going to take a quick look at the dimensionality of those data using the dim function. And we see that it's got just a little bit more than 3,600 rows and 5 columns. And let's take a quick look at what the data set looks like. So we could also access the data via the environments tab at the top right here, where you can see that I've got this cocktails listed in there. So you can see that we've got a name column, the categories. This is what we're going to be aiming to predict. We've got a row ID, an ingredient name, as well as a measure. So we're going to have to take these data and transform them into a data set that we can use for modeling. And we're going to want that data set to look like this. We're going to want to have one row for every cocktail, so one record per cocktail. And then we're going to have a selection of columns which are going to capture all of the features. And the way that I'm going to aim to do this is that features are going to be the measures of each of the individual ingredients. So for example, this first cocktail, which is records 1 through 4, it has 4 ingredients, like rum, passion fruit juice, lemon juice, and lime juice. I'm going to aim to have 4 columns in my data frame, which will give me the quantities for each of those ingredients. And of course, I'm going to do that for each of these individual cocktails. So in principle, the data frame that I'm going to end up with is going to have quite a few columns. So how do we get there? We're going to do a bit of cleanup along the way as well. And in order to make all of that possible, we're going to pull in a bunch of those packages that Astrid mentioned in her introduction. So let's load up all of those libraries. And then these are the steps that we're going to be working our way through. So firstly, we're going to work on the columns a bit. We're going to subset the columns, actually just dropping one of them, which is the name of the cocktails. We don't need that. It doesn't have any predictive value. We're also going to shuffle the columns around. I want to have the cocktail identifier on the left-hand side. We're then going to tweak the labels. So basically just changing them into categorical variables in R. We're going to clean up the ingredient names. So there are a couple of challenges with the ingredients, like there's mixed uppercase and lowercase. There are various variations on ingredients. So for example, lime juice and juice of a lime. We're then going to take a look at the measures and convert those to numerical values. You can see at the moment, these measures are actually strings that have a unit in them as well. This is not great for modeling. We're going to have to convert those into numbers. And then finally, we're going to handle any duplicates. We'll find that there are some beverages that actually have duplicate entries for ingredients. And then finally, we're going to take the data and we're going to swing it wide using one of my favorite functions. And the data will then be ready for Astrid to go ahead and build the model. So let's just remind ourselves of what the data looks like by looking at the head. So the first 6 records. This is what the data looks like at present. We don't need this name column, so we're going to drop that. And then we're going to rearrange the columns, pulling this row ID column to the front and also renaming it. And this is where I'm going to be using the pipe operation for the first time. So I'm taking my existing cocktails data frame and I'm pushing it into the pipe operator. That pipe operator is then transferring it as the first argument to the select function. So the select function is very much like the select clause or the select line in a SQL query, right? It's telling you what columns you're wanting to see. And here I'm explicitly listing the columns that I want to see and the order in which I want to see them. So ID column first. And you can see that in the process, I've also renamed row ID to simply ID. I'm taking the results of this operation and assigning it back to the same variable. So I'm basically overwriting the cocktails variable. And here you'll also see something that maybe a little bit unfamiliar if this is the first time that you've seen R, and that is the assignment operator. We could just as well use an equal sign here, but kind of the customary way of making an assignment in R is to use this assignment operator. So if I execute that and then take a look at my revised data, you can see the name column is no longer there. And I now have an ID column on the left-hand side of the data frame. This is largely cosmetic, but it makes me happy. Okay, so next step is we're going to work on the labels. So this category column on the right-hand side, this I also like to do, is the value that I'm aiming to predict should also be on the right. Okay, so I'm going to want to change the type of this column. You can see that at the moment, this column is actually a string. R has a separate data type for categorical variables, which is known as a factor. So what I'm going to do here is use the mutate operation. So mutate basically allows you to take any column in a data frame and either change that column or create a new column. I'm going to just take the category column. I'm going to wrap it in a call to the factor function, which is going to convert it into a factor, and then reassign that back to the category column again. If we just take a look at our data, you can see that the only thing that's changed is the label for this column. It's gone from being a string to being a factor, but this makes all the difference to the way that R treats the data. If we had not done this, then R, in the course of building a model, wouldn't be quite sure what type of model we're trying to build. If it sees that the column that we're trying to predict is a factor, it knows immediately that it's building a classifier. Okay, so now it's always good practice to take a look at what the relative distribution of each of the levels in the variable that you're trying to predict are. So I'm going to use the count operation, taking my cocktails data, piping into count, telling it which column I'm wanting to count. So I'm going to count the number of occurrences of each level in the category column, and I'm wanting to sort it in descending order. So in other words, the most frequently occurring categories at the top, and then going to the progressively least frequently ones. So you can see that the data set is basically dominated by these cocktail classics, and that at the bottom of the counts, we have non-alcoholic drinks, rum, shooters, etc., where there are only a few counts. Now, in principle, we could deal with the data in this current format, but it's going to be easier for us to build a model if we consolidate some of these categories, right? The more categories you have to predict, especially if those categories are sparsely populated, the harder it is to model your data. So what we're going to do is consolidate a couple of these categories together. So once again, using the mutate operation, and within mutate, I'm taking the category column and I'm piping that into factor collapse. And the factor collapse operation runs from there all the way down to there. And within that, I'm doing two things. First is to take rum and rum daiquiris and consolidate them into a single level called rum. And the other is to take these three categories and consolidate them together into a category called other. All right, so after this operation, I should have three fewer categories in my data set. And obviously the numbers in the resulting categories would have increased. I'm also going to take the whiskeys level and rename that to whiskey. This is not really necessary, but I just wanted to show you that you can also use this factor recode function to quickly and easily rename levels within a factor column. So if we now take a look at our categories, we can see that we no longer have categories with very low counts. So gin and other are still going to be a challenge, but not as bad as the challenge that we had before. So now we can turn our attention to the ingredients. And there are a couple of things that we have to do here. We're going to handle mixed case in our ingredients names, and we're also going to manage optional ingredients. You're going to see that some cocktails have ingredients that are not strictly necessary. Okay, so we're going to convert all of the ingredients to lowercase, and there's a good reason for doing this. This long and somewhat complicated operation here is basically just going and pulling out all of the ingredients that match this string orange juice, ignoring the case, and then just pulling out the ingredient column and only retaining unique results. And what we see is that we now have, within the ingredient column, 3 different variations on orange juice. So both words capitalized, only the first word capitalized, and neither word capitalized. Now, we don't want those to end up as being 3 separate features in our model. We want orange juice to just be a single feature. So what we're going to do is, once again, use the mutate operation. So take cocktails, mutate it, and inside the mutation, we're going to take our ingredient column, and we're going to call this string to lower function, which does exactly what it sounds like. It takes the strings and lowercases everything in them, and it's going to assign the results back to the ingredient column. Now, what I wanted to point out here is the very nice naming convention that's been applied in the stringer package. So this function, string to lower, comes from the stringer package, and all the functions in that package begin with str underscore. So if you know that you're going to be using a function from this package, you can just type str underscore, and RStudio very cleverly pops up all the possible options that you have. And then it's very easy, if you can't remember them all, to just find the appropriate one that you're looking for. Okay, so if we execute that now, we've got all of our ingredients are lowercased. Next thing we have to do is deal with the ingredients that are optional. And by scanning through the list of ingredients, what I found was that some of them had this term desired in them. So for example, light cream, if desired, orange bitters, if desired. So these are optional, but obviously light cream appears by itself, but we also have light cream, if desired. Ideally, we want these to end up being the same ingredient as well. So we want to deal with these optional ingredients, but there's another problem, and that is that there are, as I mentioned earlier, various different ways of describing the same ingredient. So for example, if we search for all ingredients that contain the term lemon, as well as the term juice, then this is what we find. Like lots of different variations on lemon juice. So just plain lemon juice, fresh lemon juice, juice of a lemon. These are all the same thing. Again, we don't want our model to differentiate between them. We want to consolidate these all into a single feature. Now, what we're going to do in this pipeline here is to accomplish both of these tasks, dealing with the optional ingredients as well as handling these duplicates. Once again, we start off with the data as our input. It gets piped into the mutate operation. And now we have 2 separate sets of mutations. The first is, once again, using a function from the stringer package. So string remove, again, it does exactly what it sounds like. It's going to remove a component of a string. It takes as a first argument the column that it's going to be operating on. And as the second argument, a regular expression that's going to match the components of the string that I want to remove. So I'm wanting to remove, if desired, in parentheses, if it occurs at the end of the string. Regular expressions are just so beautiful. Okay, and we're also wanting to do a replace, so string replace. And what I'm going to do here is start a list of possibly many ingredients that we might want to consolidate. So for example, here I'm replacing all occurrences of fresh orange juice with just orange juice. Similarly, every occurrence of fresh lemon juice or juice of a lemon are going to be replaced with lemon juice, etc. So, of course, these rules need to be generated by hand, and in principle, this is a rather onerous undertaking. But if you're very serious about building a good model, then these kinds of things in the data pre-processing steps are going to be super important for producing a nice, clean data set. Okay, so let's execute that as well. Everything went fine. Okay, we're getting to the end of the pre-processing stage. Don't worry, there's modeling in your immediate future. What I want to do now is take a look at the measures. So the numerical quantities that describe how much of each of these ingredients we have. I'm going to pull out the measure column from my data frame, and retain only the unique values. And let's take a look at what we have. So we've got lots of measurements in ounces. That's what this unfamiliar OZ unit looks like, means. And most of these consist of a number followed by the units. Sometimes there's a fraction. We need to deal with those fractions. We actually need to convert those into a numerical value. And then we've got a bunch of other things that are kind of a little bit more niche. So for example, 750 milliliter bottle, 3 slices, 2 dashes, etc. How can we deal with all of these things and convert them into something that's just got a number? Well, once again, we're going to have a mutate operation, and they're going to be 3 separate mutations taking place here. The first one relates to simply converting the numbers, like the fractions, into their numerical equivalent. And here you can see like really a beautiful application of the pipe, right? I'm taking my measure column and I'm piping it into the first occurrence of this string replace function. And this is simply replacing the string 1/4 by 0.25. And then the result of that is now being piped into another operation, which is going to handle the thirds and then the halves, the 2/3, etc. So by the end of this pipeline, all of those fractions will have been replaced by their decimal equivalents. It'll still be a string, but at least it'll be a decimal string. The next thing we want to do is handle this item for the glass. And this seems to occur in ingredients where it says like add 1 pickled onion or 1 cherry for the glass. We don't want to have the for glass classifier. So we simply replace that by 1, because generally it's going to be 1 pickled onion or 1 cherry. And then finally, we're going to strip the units off the end, right? We're only wanting to have a number left in those columns. So once again, using string replace and a regular expression that's going to basically match the majority of these. It's not going to match all of them. So for example, 1 750 mil, I'm not entirely sure how to deal with that. Should I make it 1 or should I make it 750? So I'm going to just neglect that for the moment. We run that and take a look at our data again, and we see that that measure column now has literally numbers in it. We can take a look at the relative frequency of those, and we can see that like regular numbers seem to occur fairly frequently. We've got no number at all, but that only occurs once. We've got some occasions where we've got numbers that are not really a single number. This one, for example, we could fix quite easily. 2 bottles. I suppose I could also have included bottles in this list of replacements. I'm not going to do that for the moment. What we want to do now is take this column of numbers as strings and convert those into actual numbers, which are going to be useful for machine learning. Again, a mutate pipeline, and I'm going to take my measure column and I'm going to pass it through the as numeric function. I'm wrapping that in the suppress warnings function. Why? Because this as numeric function, whenever it encounters a value that it can't coerce into a numeric, for example, 2 bottles, it's going to return an NA, and it's also going to issue a warning. I understand where these warnings are coming from, so I'm suppressing them, but I acknowledge that they're going to be NAs in my output. The way that I'm going to deal with this, because they only form a relatively small proportion of my data set, is simply to drop them. So this drop NA is going to remove all of the records from my data set that actually contain NA values in that measure column. Okay, handling duplicates. Well, some cocktails, like this one, for example, have duplicate entries for the same ingredient. So I have 2 measures of vodka and then another 2 measures of vodka. And it's not readily apparent based on the ingredients what's happening here. Is this the case that they've actually just duplicated the ingredient in the recipe and they only meant that it was 2 measures of vodka? Or do they mean add 2 measures of vodka, then add lemon juice, then add another 2 measures of vodka? It's not clear. I think that personally the second approach is probably the better one. Anyway, we don't know, right? So we have a couple of ways of consolidating these numbers. We could add them, we could take the smallest, we could take the largest, or we could just average. I think that the conservative approach here is to average them. So what I'm going to do is take the data, I'm going to group it by ID, ingredient, and category. So basically narrowing down to everything except the ingredient. And then I'm going to summarize. I'm going to take the mean of the measure. So in this case, what's going to happen is I'm grouping by everything else except for the ingredient and the measure. And I'm going to average the measure, which means I'm going to end up with just a value of 2. All right, so after that operation now, I end up with just a single entry for vodka and that particular cocktail. Right, and now the final and my favorite ingredient, and that is taking these data and spreading it wide. So Astrid mentioned in the beginning of this talk that we're aiming to have tidy data, and in tidy data you have one record per observation and one column for each of the features in that observation. Our data at the moment is precisely like that. However, we don't want to have tidy data for modeling. We actually want to take these data and fling it wide so that we have one column for each of the individual ingredients. And within those columns, I want to just see the measure values. So how are we going to do that? Using the pivot wider function from the tidier package. So there are 2 pivot functions. There's pivot wider and pivot longer. Pivot wider does exactly what it sounds like it does. Right? It takes your long data and swings it out into a wide format. Pivot longer will take your wide data and transform it into long format. Pivot wider needs at least 2 arguments, names from and values from. So I'm specifying names are coming from the ingredient column and values are coming from the measure column. And what this means is that in the data set that we're generating, there's going to be a column with a name that's derived from the ingredient column. So in other words, I'm going to have a column called lemon juice. I'm going to have a column called simple syrup, another column called vodka, etc. And in each of those columns, the value is going to come from the measure column. So for example, in the lemon juice column, for this particular cocktail, I expect to see a value of 0.75. Obviously, we're going to end up with a very large number of columns, and some of these columns are going to be sparsely populated. So I'm going to specify values fill is 0. If a particular ingredient is not used for a particular cocktail, then the amount is 0. Right, so we can take a look at our wide data now and see we still have our ID column, we've got our category column, but now we have all of these columns stretching very, very wide, which give the quantities for each of these individual ingredients. So 1 quantity of lemon juice, 2 quantities of light rum, etc. Okay, so let's take a look at the column names. These column names are a little problematic in the sense that they have punctuation and they also have spaces. This makes them a little bit difficult to work with in R. So we got to use this clean names function from the janitor package. And what that does is it removes all of the punctuation and it replaces spaces with underscores. So if we have a look at those names now, you can see that they're nice and tidy with these underscores where they were placed spaces before. Finally, we still have this ID column. Now the ID column can actually really screw up your model. It has no predictive value. So we're going to simply set it to null and it will then be removed from the wide data set. And this data set is then ready for modeling. And with that, Astrid, back to you.
Great. So now we want to get into our model building process. So we've done our data import, we've done our cleaning, and now we're going to get into actually creating our model. So I just created this very basic little pipeline to show you sort of how this situation works. So here we will go from data cleaning into variable selection and pre-processing. We're going to just model all our variables tonight, but you can obviously tweak those. Pre-processing, we're going to do test, train, split, cross-validation. We're going to select some models, and then we're going to tune hyperparameters and evaluate our models. And for those of you who do this, you know that this is an iterative process. Like every part of this pipeline are little points that you can tweak and change things around. So Tidyverse and TidyModels are really designed to make this iteration process as sort of painless and human readable as possible. So the TidyModels, again, is like a mothership with its little baby packages. These are all of the TidyModels packages, and we'll be using all of them today. Cool. So our sample allows you to create test train splits, cross-validation folds, bootstraps, and a lot more. Recipes allow us to string together multiple pre-processing steps and the model instructions before you actually create the model. So here you can basically create a flow of pre-processing instructions, so like scaling, normalizing, so that every time you add a model to this sort of pre-processing step workflow, it's consistent between the models. Parsnip, I'm going to read this, provides a tidy unified interface to models that can be used to try a range of models without getting bogged down in the syntactical minutiae of the underlying packages. So what this means is that before, in the past, in the dark days of before, you would need to import several packages and run several formulae with different arguments. So for example, if you wanted to do a random forest in R, you had several packages to choose from. Here's 3. So random forest, ranger, and sparkly R. And they each have their own random forest function. And they each have their own arguments. So for example, here, the number of trees is specified by ntree. Here it's specified by num.trees. Here it's specified by num.trees as well. But now you only need parsnip and the name of the package. So the arguments are actually standardized. So when you want to run a Spark random forest, you basically need to just switch out this argument here within a set engine function call, and you can run a Spark. If you want to run a ranger random forest, you just have to swap out the Spark word for random forest. And the arguments are sort of the same no matter what kind of random forest you want to do. So that's pretty slick. Tune allows us to tune hyperparameters. Yardstick allows us to determine how well a model has performed. So this is for our model evaluation stage. So it has root mean squared error, RAC, area under curve, accuracy, etc. And workflows are super great. It's basically an object that you can use to bundle together your pre-processing modeling and post-processing requests. And we'll see now when we get into the code like why that's super useful. Cool, so let's actually do some modeling before we get into that. Cool. So I've sourced Andrew's pre-processing files. I think we're going to share the repo with you guys after this. I think Andrew just needs to set it to public. Nudges Andrew gently.
For sure.
You'll notice that there's a third file, which is the old way of doing some classification. So the third file is called O3 Old School. If you're interested in how people can and still do classification with the caret package, you're welcome to go and dig into that file. But in the interest of time, I'm just going to go straight for the TidyModels approach. Cool, so we're going to import TidyModels. Because we're using all of the packages, we'll just call library TidyModels. Just to remind us of what our data looks like, I've just got an account again of all of the levels, all the categories we have. And you can see, cocktail classics is overrepresented, other is underrepresented. So we have different levels of representation in each category, and we need to sort of account for that when we do our modeling. So a super fun and easy way to do that is to just specify that the initial test train split must consider that as a factor. And when we call initial split on our Y data frame, we can set the strata argument to specify the category. So now it will go into that category, and split them sort of equally between or proportionally, let's put it that way, between the test and the train data sets, which is super nice. Okay, so the default proportion is 3/4. I just want to make it explicit. So we run that. And to extract our training set, we just run training on it. And to extract our test set, we just run testing on it. Cool, so we're gonna actually build our models and test them first using cross-validation. So there's this super nice little function also within the R sample package where you can specify your training set or any set you want to use cross-validation in, the number of folds, and again, I'm going to set strata to category for the exact same reason as we did for the test train split. So if we look at our folds, we can see we have these nested data frames within, or nested tibbles within this tibble. So for fold 1, we have a split of 667 are in the train and 75 on the test. And you can see that kind of consistent numbers for each fold. So that looks cute. Now we're going to specify our models. So with Parsnip, you would basically create this little workflow. Well, it's not quite a workflow yet, but it's our model, I suppose. Where you specify, some of my screen's doing weird things, which function you're going to use. So it's the Parsnip function. You specify the engine. So like I mentioned in the slides, here we'll be using the rpart package decision tree. And you set the mode to classification. So obviously if you're doing regression, you would set it to regression. So we'll just run that and have a look at tree model, and it's nothing. It's basically an object that just has the instructions for what we're going to fit it. Cool, and we're going to compare a decision tree model to a random forest model. And I'm using Ranger and basically also just setting the mode again. Ooh, excuse me. Great, so here we go into workflows, why workflows are super dope. So now we're going to specify the workflow that we're going to use for the pre-processing of our data before we fit our model itself. And this workflow is super nice because it's portable between the two models that we've specified. So we'll use this workflow to both fit the data to the forest and to the decision tree. Cool, so we specify a workflow. Here, this add formula function allows you to specify the target variable. So here we're specifying the target variable is supposed to be a function of everything else. This dot refers to everything. So everything being all of the other columns in the data frame that we're providing to this workflow. Then we're going to do 3 steps. So these steps are part of recipes. So here we're going to center our data, we're going to scale it, and we're going to remove columns that have 0 variance. So we're just doing a little bit of sort of cleaning and selection over here. And we're using this all predictors function to specify everything that's not the category column, which we specified in formula, is going to be used, is going to be centered, scaled, and removed if it's got 0 variance. So let's run that. And again, that workflow hasn't done anything. It's literally just outlined the steps for the process. Cool, so let's train our first model. We're going to do this results tree is going to be the name of our object that we create. We're going to take our workflow and slap on our model. And then we're going to fit our data. So if you don't want to do any cross-validation, you can just use the fit function as is. And specify train as the argument to fit. And that would be perfectly fine, but because we're using cross-validation, we want to use this fit resamples function. And our resamples are going to be our folds that we created earlier. And then if you want to save your actual, the predictors from this process, you can specify a control argument. So that's what we did here. So if we want to train our model, you can see it's running on the first fold. Every time you see this fold, a warning with a little exclamation point, it's complaining about something. So here it's complaining that no observations were detected in truth for levels other. So what that means is that within this fold, there was no drinks that were in the category of other. So we already accepted up front that this model isn't going to be great at sort of categorizing drinks that are, you know, potentially other, because we had so few other drinks. And gin, same for gin. If we went up and looked at our gin, was just only 17 cocktails were gin cocktails. So that's expected. Cool. So let's have a look at our results tree. So let me comment that. Oh, whoopsie. Stop. Okay, results tree. Oh my gosh, stop. Wonk, wonk. Excuse me, guys. Oh, now you get to see my hideous uncurated no project zone in our studio. Cool. Do we have any environments? No. Source that one. Dope. Okay, we are back in business. Just give me a seckie. Let's just rerun our tree. Let's run up till late. Please don't crash on me again. Love you. Okay, she's running. Take this moment to go grab a drink if you need one. Takes big swig of cocktail. Cool. So if we have a look at our results for the decision tree, we can see again we have these nested tibbles within our tibble. So each row here is a fold, and within that fold we have our splits. We have our metrics, notes, and predictions. So notes will only show up if that fold was complaining about not having a category level. And our predictions will be basically the little split within our cross-validation predictions for those. So I'm just going to see here if I can unnest one of them. Incompatible lengths. Okay, let's just unfold and nest that one. Cool. So here we've got metrics for the first fold. So this is our fold number 1, and we can see we have an accuracy and an area under curve estimate for for the first fold. So that's how you can dig into how each folds model is actually performing. So pretty cool. Great. Okay, so let's run the random forest. And it's going to basically do the same thing again, but for our forest. And we'll probably expect our random forest to do slightly better than our decision tree, because as some of you may know, a random forest is just many, many decision trees together, and then average is taken for the predictions of each decision tree. Cool. Great. So Yardstick is fantastic because you can just use this beautiful little collect metrics function and basically extract the metrics, the performance metrics of your model training. So whereas before I had to sort of unnest and go and look for things within that fold, this collect metrics will just give it to you as an average of all of your folds. Super nice. Great, so we've got our tree and we've got our forest. And as expected, our forest has been slightly better if we look at the ROC, AUC and the accuracy, slightly better than for our decision tree. What's also nice is that you can get something like sort of like a long format confusion matrix using this confirmatory sampled function. And basically what it gives you is these columns with the prediction for that category, the truth, so what it actually is, and then the frequency of that observation. So for example, here we have the truth being brandy and the prediction being brandy occurred not at all. So our model was not very good at predicting whether a brandy cocktail was in the set. But if we scroll down to cocktail classics and look within this class, you can see that we got a higher frequency for the cocktail classics. So it's important to note that these frequencies can't be compared between groups, but only within a category. So it's kind of a slightly different long format confusion matrix, but I think quite intuitive as a human reading that. Great, so we can do the same for the forest. And if we want to collect our predictions, we can do that using this collect predictions function. Super nice. You can see for each fold how the decision was made for a particular observation. So for this first observation, we can see that the decision that was made was rum. So it was predicted to be a rum class. That was incorrect. It was actually a classic cocktail, but it will have the probability in the rum column being the highest. So that's how it actually makes its decision based on probability. Cool, so now we kind of have an overview of how TidyModels work. I just want to back it up a little bit and just reiterate how lovely it is to have a workflow that you can port between models and use cross-validation to actually compare models that have been normalized and standardized in the same way. Super powerful. Cool. Okay, on to hyperparameter tuning. If we have time, is it okay if we go a little bit over? Cool. If anyone needs to bounce, I will not be salty. Great. I'm just going to run lines 11 to 30 so long because they take a little bit of time, but I will walk through each one. Okay, so hyperparameter tuning we do with this tune package. So shock horror over there. So oftentimes a random forest is totally feasible and lovely, but sometimes maybe you want to actually create a visualization of your decision tree. We'll rather use a decision tree because it's slightly simpler and more easy to explain to somebody who isn't an ML expert. But you kind of want to try and get the best decision tree that you can, and using something like Tune is really nice for that. So we're going to take our, basically take our workflow, not our workflow, our, I suppose it is a workflow in its own way, but it is not a workflow TM. Our actual model creation workflow over here. And we're going to specify decision tree, again, set engine, set mode. The only difference is this time, we're going to add this tune argument to each of the hyperparameters that we want to tune. So we want to find the best combination of hyperparameters to use for this particular model. So you would specify the cost complexity parameter within the decision tree as a tune function, and the tree depth as a tune function. And then later on, you create this grid where you specify the cost complexity as a function, which it's referring back to our decision tree, and our tree depth, again, as a function. So those two will be related to one another. And if we have a look at, I don't know if it's going to let me look at it. Oh, crash. Let me see here. Tree grid. Has it made it? No. Basically, it combines all of the potential combinations. Here we specified levels equals 5. So we're taking 5 values for cost complexity and 5 values for tree depth, and we're making every possible combination of all of them and putting them into a grid, which we'll then call when we actually create our model. Okay, since this is still running, despite the fact that I'm done talking about it. Oh no, I'm not done talking about it. Okay, Cool. So when we actually come to making our tuned tree, we are going to specify the same workflow as before. So the workflow from the previous R script that we used. Here we're going to, again, add our new model, but it has now new model parameters. And we're going to add something called a tune grid, which will have our folds as resamples and our tree grid, which we created over here, which I'll show you in a moment, to actually specify the tuning parameters for this model. This will all make sense when she stops running. While she's running, I'm going to just back up to the slides, and hopefully this last slide will help kind of solidify this whirlwind tour of Tidyverse and TidyModels into something sort of cohesive that you can take forward with you from this talk. So backing up, we started with data import with readr, data cleaning with tidyr, dplyr, forcats, and stringer. And we used maybe like dplyr for some variable selection over there. We did some pre-processing steps with recipes and R sample. So R sample, we did our splits and our folds. Recipes, we did our normalization and our centering. To create our models, we used this parsnip package, which you can just specify the engine for the model referring to another package that contains that model function. Then for tuning our hyperparameters, we are currently using tune. And then to evaluate our models, we're using Yardstick and ggplot2. And all of that is bundled together within workflows to make it portable. And then the sort of through line through all of this is our pipe operator from the Mutate package. Cool. Let me see if my code is done. Oh no! Sorry, it took like 3 minutes the first time I ran it, and now it's still done. Does anybody have questions so far? Because this would be a good time maybe to take some.
Maybe I have a question. Like you said that the old one was longer. It would be interesting maybe just for you to just show us, or if there's time, just like how different it is.
Old school version.
Yeah.
Interestingly, the old school version is not necessarily longer, but it is less, maybe less readable and less kind of transferable between packages. But Andrew, this is your code, so maybe you should explain this.
Yeah, for sure. So the precursor to parsnip was known as caret, as you can see at the top of the script. And the principle behind caret was that the aim was to have a single package which would allow you to access a very wide range of models. And to that end, caret is actually still way ahead of TidyModels, because I think caret has got a couple of 100 models embedded in it. Some of those models are very obscure indeed. But the principle is much the same in the sense that it provides a uniform interface, and everything centers around this train function, which you can see has been invoked on line 12 there. And the interface is much the same as what you've seen already this evening. So the first line is specifying the model function, so what you're predicting as a function of what else. So in this case, category is a function of everything else, and then where's the data coming from? And then sort of the key to the way that caret works is at line 15, where you specify the method. And you can consult the documentation for the train function to see just exactly how many methods are available. There are a lot of them. And then lines 17 through 19 are in a very kind of concise way capturing what Astrid has just been showing you for the hap parameter, with the hap parameter tuning. So you've got this tuning grid. In this case, the grid just consists of a single element, but in principle, you can have you can list multiple parameters in there, and you can have multiple values for each of those parameters, and that tuning grid will then iterate your model over all those various combinations of the different parameter values in the grid. And then the final component there is the training control, and that just specifies exactly how the cross-validation or bootstrap validation is going to occur within your model. So yes, on the one hand, it is a bit more concise than what Astrid has been showing you, but at the same time, we've kind of been fleshing this out into lots of individual parts so that you can basically understand each of those parts in isolation. You could
also think
do
that
the classifier and the tuning in a much more concise way. Sorry, Astrid.
Definitely. And I also think if you want to basically run the same pre-processing and run like 10 different models, Tidyverse will be more concise because you'll have your pre-processing and your folds and things done up front, and then you can run different models later on.
Definitely. So, and also the train function doesn't play nicely with the pipe, and you can see that because its data argument is actually the second argument. Astrid, if you at some stage can flip back to the old school script. So you can see there that the data argument is the second argument to train. Now you can definitely deal with that using a pipe, but it's not very convenient. Normally, if you're wanting to pipe into a function, you want the data to be the first argument. Sorry.
Cool. Okay, so we have our grid, which we finally. Okay. Andrew warned me that this would happen. I shall heed his warnings next time. Cool. So I just wanted to show that this grid is basically 5 different values of cost complexity and 5 different tree depths, basically repeated in different combinations with one another. And this is what's fed into our tune grid along with our resamples. So let's see how our tuned tree did. We can use this collect metrics function again, super handy. And we've got 50 rows because we have 2 metrics that we're interested in, accuracy and area under the curve, for 25 models, because we'll have 25 combinations of our hyperparameters. We can visualize this with ggplot. Not going to go into the detail there, but basically this shows that as you increase the cost complexity, the area under the curve and the accuracy of the model goes down. And so for area under the curve, a tree depth of 15 is good, whereas oh no, this one actually is pretty consistent between those. Yeah, so a higher tree depth is maybe better for our purposes. Cool. So you can now show the best trees. So here we'll be using the ROCAC parameter to give us the best curve, but you could specify accuracy or whatever other metrics that you're interested in. And you can select the best tree as well. So here we've said show best, and that gives you the best 5, and select best will give you the top one out of all of them. So our best tree has a cost complexity of that and a tree depth of 15. And bearing that in mind, we're going to decide to use this tree, these parameters to create our final fit. So yeah, so here we'll just specify last tree as our model to apply to the training data. And we'll specify the cost complexity and tree depth that we decided were the best after tuning, our engine, our mode, and we'll run that. Have class models, yeah. Okay, weird. Cool, and let's run that. So while this is running, we're taking the exact same workflow as before, and we're adding our model. And this last fit we're doing, we're using last fit here instead of fit or fit, what was the other one? Fit resamples. Here we're using last fit because we're going to actually use all of the data. So we're using the test and train data that we created with our data split. So there isn't any cross-validation going on here. And then we'll collect our metrics for our last model. Let's see, is it slightly better than our previous model? So it would appear. Not quite as good as random forest, but slightly better than our first decision tree. Cool. So just to sort of summarize this situation, I think having that portable workflow that we could use between tuning and applying different models, super useful. Okay, I just wanted to say in the slides, there's a nice slide for learning more. So within the Tidyverse, there are great resources online. I highly recommend, if you're new to R and you kind of want to get a feel for it without committing to installing RStudio, these RStudio Cloud Primers are super great. You basically interact with R in a little cloud-based questions and answer kind of situation, like a really nice gateway drug to R. And TidyModels, Julia Silye, she has the best tutorials, explanations, blog ever, so go and check that out. And then as Andrew mentioned, the Tidy Tuesday GitHub repo and the online community are fantastic. Cool, that's it.